Very good afternoon to everyone. This is Shubhangi Rao. I'm working as an assistant professor at MLR Institute of Technology. And today we are going to discuss about a very important topic, conduction and convection currents. So let's start. So before going to conduction and convection currents, let's first discuss what is current. So current through a given area is basically the electric charge passing through the area per unit time. The formula says I is equals to dq by dt. Electric charge passing through area per unit time. And the unit of current is amperes. We can also say that 1 ampere current is produced if the charge is transferred at the rate of 1 coulomb per second. This is also one more definition of current. And the concept of current density will be very useful in defining the events occurring at a point. So this Jn is given as current density, which says current passing through per unit area, del I by del S. Also you can write del I is equals to Jn del S, right? And this current density is always perpendicular to the surface. We can consider this. So we know that it will always be perpendicular to the surface. If it is not perpendicular or if it is not normal to the surface, if it is making some angle theta with the normal, but still as we know that it should be perpendicular to the surface, so this component can be taken as j cos theta, because as we know it is normal to the surface. So when we put it here, it becomes j cos theta del S, and further solving it we get j dot del S, and this current formula becomes integration of j dot ds. So this was about current and current density. Now we will specifically discuss about convection currents and conduction current. So first we will discuss about convection current. So what is convection current? So basically convection current will be produced when current flows through an insulating medium. For example, liquid, rarefied gases or vacuum. By these examples we can understand that convection currents do not involve conductors. They don't need conductors. So we can also say that it does not satisfy Ohm's law. Let us take one example of convection current. A beam of electron in a vacuum tube. It's an example of convection current. Right. So to understand it further, we are going to consider a system. Here in this rectangular block, you can say we are taking a small area here, small volume here, where the surface area is del S. The volume charge density is rho v, and the length of this part is del L. This is the velocity of charge, and this is the y direction. Now we will consider this system and we will find out convection current density. So we are considering a beam of electron with volume charge density rho v, and it is flowing in y direction with the velocity uy. Why we are taking? Because we are considering y direction. So this u can be written as uy ay, where ay is the unit vector in y direction. Now the current through the filament can be written as del I is equals to del q by del t, and in place of q we can write rho v dv. So rho v is the volume charge density, dv is the volume. So this dv can be written as del v can be written as del s, del x, del y, del z. So if you notice here, this we can take in y direction del L, and this can be considered as del S. So basically del V can be written as this del S del L, because it is basically what? Del X, del Y, del Z. So this is for y direction, and the remaining two del X, del Z can be written as del S. So now this can be written as rho V del S del L upon del T. Further solving it, further simplifying it, we get rho V del S, and we can take it as del L by del T, which is nothing but the velocity, and because we are taking y direction, this can be written as uy. So this becomes rho V del S UV. Now the y directed current density Jy can be given by this formula. Jy is equals to del I by del S. So the formula which we are getting is rho V Uy, or in general we can say J is equals to rho V U. This y we are taking for y direction, it can also be taken in x and z direction. So our convection current density can be given by J is equals to rho V U. So this was about convection current and convection current density. Now we will discuss about conduction currents. As we have discussed in convection current, it does not require conductor because we can take example as vacuum tube. But when we talk about conduction current, we must understand this difference. Conduction current requires a conductor as a medium. And the conductor contains large number of free electrons that provide conduction current due to impressed electric field. So whenever an electric field E is applied, the force on electron with charge E is given by F is equals to minus EE. And also we know that electron is not in free space, it will not be accelerated under the influence of electric field, and it will suffer constant collision with atomic lattice and will drift from one atom to another atom. Now if electron is having mass m and it is moving in electric field E with some average drift velocity u, the average change in the momentum of free electron must match the applied force. So according to Newton's law, we can write it as mu by tau is equals to EE. And further solving it, we can get u is equals to minus E tau upon me, where tau is the average time interval between the collision. This indicates that the drift velocity is directly proportional to the applied field. And if there are n electrons per unit volume, the electronic charge density can be given by rho v is equals to minus Ne. Also we know that convection current density is J is equals to rho v u. And if we see this formula, J is equals to, we are getting Ne square tau upon Me, we get J is equals to sigma E, where sigma is Ne square tau upon M, which is known as conductivity. And this formula which we have written here, this is called point form of Ohm's law. J is equals to sigma E. So this was about convection and conduction current. Also we included some discussion about currents and current density. In case of any query, please write to us. Thank you very much.